Hey everyone, welcome to Online Learning Week 2. Today we're going to be focusing on calorimetry. Calorimetry is an important experimental determination for enthalpy in chemistry. So calorimetry uses a calorimeter, which is a very insulated container used to measure the heat changes of a system without much heat loss to the surroundings. It can be used to determine the specific heat of a substance. That's one use. There's plenty of different uses for a calorimeter, depending on what information you have and what you're trying to solve for. So this is a poor man's version of a calorimeter. Two basically coffee cups with something on top. If we were in class, we'd be doing this with 2 coffee cups and a piece of cardboard. And then you've got a thermometer because you need to know the temperature, and then you've got something in there to stir it. Usually we just use the thermometer to stir it. I'm going to be posting in the assignments this week the stuff from the homework packet, yes, but I'm also going to have you do an online calorimetry lab and have the information and a link in that assignment. So do that. It'll be a good experience for you to see how it works. So how a calorimeter works. So it says measure the volume and temperature of the water sitting in the calorimeter. So you start coffee cup, add a certain amount of water to it, you know the volume, and then you take the temperature of it. So we're going to find the mass of the object that you're trying to determine the specific heat for, so a piece of metal. So what you do is you heat up the object to determine the temperature before placing it into a calorimeter. If we were going to do an experiment like this, we'd get a big test tube, put the piece of metal in it, and then put that in boiling water, and then we would know that the initial temperature of the calorimeter would be 100 degrees Celsius. And then what you need to do is, this needs to happen very quickly. You take that piece of metal that you've warmed up, put it into the calorimeter, close the lid, stir it up, and you're measuring the water until the temperature, until it stops, till it reaches the highest. And then you can do your calculations to determine the specific heat. It's important to note this critical information here. It says, understand that the heat gained by the water was lost by the object. So in this example, you've got a hot piece of metal going into water that's cooler. So what's happening is the metal is giving off that heat. That heat has to go somewhere. The water absorbs it. When we do calorimetry calculations, we assume that all of the energy goes into the water and that no energy is lost. That obviously is not true. If you take a piece of metal and you have to carry it through the air and put it into the water, you're going to lose some of that energy. Also, 2 coffee cups with a piece of cardboard on it are not going to hold in that heat very well. So we just assume that all of the energy goes. So let's look at some problems that we could possibly be doing with this. So a calorimeter with 100 grams of water is at 26 degrees Celsius when a 32.6 gram piece of metal at 98.3 degrees Celsius is added. What is the specific heat of the metal if the final water is 47 degrees Celsius? So when we do a calorimetry problem, we always start by determining the Q of the water. The reason why, and this is very important, I always know all of the information about the water. I'm measuring the temperature of the water, I know how much water I have, and most importantly, I know the specific heat of water. So for this one, the Q of the water is going to be, we got the mass, so that's 100. I'm going to put a decimal there so I can have 3 sig figs, grams. Times, we know the specific heat of the water is 4.184 joules over grams degrees Celsius, times the change in temperature. And remember, change in temperature is always the final minus the initial. So the final temperature of the water is 47 degrees Celsius, and I started at 26. So 47 minus 26. I do this math. The Q of the water is going to be 8786.4 joules. I'm going to put that into sig figs. It's going to end up being 8,800 joules. So that's the Q of the water. Now, and notice that the sign is positive. That's because the water absorbed it. It was endothermic. Where did that heat come from? It came from the metal. The important part, whatever the water does, in this case, the metal, does the opposite. So the sign of that is going to be the opposite. So the Q of the metal, we know is going to be negative 8,800. I know the mass, 98 point, no, that's the temperature, 32.6. 32.6 grams times C, which is what I'm trying to find, times what's the final temperature of the water? So, I mean, of the metal, sorry. And the answer is the final temperature of the water. They're in there at the same temperature, okay? So they have come to an equilibrium. So they're at the same temperature. So the final temperature of the metal is the same as the final temperature of the water. It's like you have a hot cup of coffee, you put a spoon in it. Well, energy goes from the hot coffee into the colder spoon until they reach the same temperature. So that's going to be 47 minus 98.3 degrees. And that's important. I need it to be negative because my C's are never negative. I'm going to end up doing a negative here divided by a negative there. And when you do this math, your C for this metal ends up being 5.3, and the units joules per grams degrees Celsius. Okay. So I found the specific heat of that metal. I'm going to clear this. So pause it if you need to get all that information. Yeah, feel free to pause, rewind, whatever you need. Example 2, a calorimeter with 150 kilograms of water. I'm going to just turn that into grams. Is at 22.3 degrees Celsius when a chunk of copper at 102.35 degrees Celsius is added. If the specific heat of copper is 0.385 joules per grams degrees Celsius and the final water temperature is 26.7, how big was the chunk of the metal? Calorimeter problem, we still need to start with the Q of the water. So I have a lot of water, 150,000 grams. I still know what the C is, 4.184 joules over grams degrees Celsius. And then the change in temperature. So the final water temperature says 26.7 minus my initial was 22.3 degrees Celsius. When I do this math with the correct number of sig figs, my Q for the water, 2.8 times 10 to the 6th joule. So that's a big number. So then if I want to do the metal, remember, whatever the water does, the thing inside the water, which I'm just going to call the reaction, in this case, it is a metal, does the opposite. So negative 2.8 times 10 to the 6th joule is equal to, I do not know the mass. I know the specific heat, 0.385 joules over grams degrees Celsius. And let's see, the final water temperature, which is the same as the final metal temperature, 26.7 minus 102.35. You do that math, the mass ends up being 9.6 times 10 to the 4th grams. Okay. So same idea with a calorimeter. I'm not finding the specific heat. In this case, I was finding how big is the metal. Okay. And then the last question here isn't really a calorimeter question, so I don't know why I put it here, but it's still good review. Calculate the temp change. 175 milliliters of water is changed by adding 122.3 kilojoules. I'm going to change that kilojoules into joules because my C for water, 4.184 joules over grams degrees Celsius. So I want this to be 2 zeros. So I want that to be in joules as well. So I'm just going to be using my MCAT, Q equals MC delta T. I know that I have 122,300 joules is going to be equal to 175 grams. Remember, for water, 1 gram equals 1 milliliter for water times the 4.184 times the change in temperature. Okay, just do that math. Your delta T is going to give you 167 degrees Celsius. Okay, let's clear this. And then the last slide for this week is, so the 2 coffee cups was the poor man's calorimeter. A bomb calorimeter is the expensive version. Even in my university, we did not have one of these. In my class, we did use 2 coffee cups with a piece of styrofoam on top, or a piece of cardboard on top. But this bomb calorimeter, you can see just from this diagram, is way more insulated. So what's important about this is that you can actually calculate the amount of energy that the bomb calorimeter absorbed, okay? So this equation, Q reaction is equal to Q water plus Q bomb. We need to make sure we know that the reaction will be negative, because what's happening is inside, you're always igniting it. And when you ignite it, you're going to have a negative. It's going to be exothermic. So we've got 0.444 grams of C12H22O11 is combusted in a bomb calorimeter containing 748 grams of water that changed from 20 degrees Celsius to 22.06 degrees Celsius. The heat capacity of the calorimeter is 0.420 kilojoules per degree Celsius. Calculate the heat of combustion in kilojoules per mole. Let's do the easy part first and do the Q of the bomb. So the energy from the bomb calorimeter is just equal to the heat capacity, so 0.420 kilojoules per degree Celsius times the change in temperature, which was 2.06 degrees Celsius. So you do that math, and the Q of the bomb is 0.865 kilojoules. So that's how much energy the calorimeter itself absorbed. So now we can figure out for the water. So it had 748 grams times the 4.184, which is the specific heat of water, times the change in temperature, which we did already, which was 2.06 degrees Celsius. And so that will give me 6450 joules, which is 6.45 kilojoules. So I've got this, I've got this. To find the Q of the reaction, it's going to be a negative of the 6.45 kilojoules plus the 0.865 kilojoules, which gives me negative 7.32 kilojoules. But, and I apparently left this out when I was actually doing these problems, it wants to know the heat of combustion in kilojoules per mole. So I have to take this answer and divide by the number of moles. So I'm going to erase a little bit of this. I'm going to erase this part over here above the bomb so I can determine the molar mass and determine how many moles that is. So I've got C12 H22 and then O11. Oops. I'm going to add all those up. and that's my molar mass. And then I'm going to take my 0.444 grams, 1 mole, 342.28. And that's going to give me, I'm going to replace this with the actual number of moles. 1.2, well, I'm going to round that up to 3 times 10 to the negative third moles. And then I'm just going to do the division. 7.32 divided by 1.30 to the negative third. And I should get, as my answer, the heat of combustion is going to be negative 5,630 kilojoules per mole. Okay. Sorry, I forgot to do that part, so it took a little longer than everything else, but that's all of the notes for this week. Please make sure that you go back, rewind, pause, see if you have any questions, and then look on the assignments to see what to work on in the homework packet and to get more information on that calorimetry online lab. Okay, I'll see you next week.